Welcome back, Algebra 2 students. There's Algebra 2. In this video, I'm going to actually combine 6.6 and 6.7 in this video, just because there's not a ton of stuff in 6.7 that's brand new for us. And so I figured rather than do a short video, we'll just kind of combine the two and I'll do a couple extra problems. To be honest with you, what we're going to do here is we're going to go through a lot of examples. And so all of this is revolving around solving equations and checking for extraneous solutions. So I'm going to do all of the problems that are on page 182. And so what I'm going to do first is I'm going to go through and do all the odd problems, all right? So on the video, I'm going to do through all the odd problems. And then what I would recommend that you do is you pause the video and try all of the even problems on your own, and then come back to the video, unpause it, and then I will do all the even problems on the video as well so you can check your answers. That's just my suggestion, you know, that way you're not... That way you can kind of practice some of these skills without having just to watch me do all of them, because it's going to be important that you're obviously able to do this, okay? So let's start by doing all of the odd problems together. That should give us a good overview of kind of each type of problem. So again, I'm on page 182 on lesson 6.6. All right, so in the first couple ones, these were like ones we did in the rational exponents unit. So we have to get these to have the same base. In number one, they already have the same base, so right? They're both 5s. So in this case, this is actually a fairly simple problem. All we have to do here is set our exponents equal to each other and solve for x. So I'm gonna add 8 to both sides and subtract 2x. I get x to equal 4. You should always check your work just to make sure that your answers are correct. Really, the extraneous solutions come into play with log functions, and so we're not as concerned about exponentials, but notice that this is an exponential, not a log. All right, number 3. So I'm going to go through the odd ones. So notice that this one doesn't have the same base. And actually, there's an exponential on this side, but no exponential on this side, right? It's just 5. And so we can't really get 3 and 5 to have the same base. So our strategy here is to do the inverse operations. This is kind of the big thing that we've talked about all unit long, like how logs and exponentials are related to each other. And so the inverse, so if I were to ask you to solve an equation, right? And I said, x squared equals 36. And you would tell me, okay, I would square root both sides. And the reason you're square rooting both sides is because the square root is an inverse operation of a squared or of a quadratic. So that's why you're doing this, right? That's why you're square rooting both sides. So not only so that this will cancel out and give me x equals plus 6, but more importantly is that those are inverse operations. So if I have an exponential where the variable is in the exponent, the only way I'm going to get this exponent or this variable out of the exponent is to undo the exponential. So if I have an exponential with a base of 3, its inverse is a log with a base of 3. So I'm going to log base 3 both sides of my equation. Just like up here where I square rooted both sides of my equation because I wanted to get rid of the square, right? So to get rid of the exponential, I'm going to log base 3 both sides of my equation. So log base 3, and this is not this is like 3 to the x plus 3, and this is log base 3 of 5. The reason we do this is so that those cancel out. So remember, those are inverse operations, a log with a base of 3 and an exponential with a base of 3. So I get x plus 3 on that side of my equation. Now you can throw this into your calculator. You can either use change of base formula or you can just use the math feature. So log base 3 of 5. Let's round to 3 decimal places. That seems to be what Big Ideas is doing. So I got 1.465. And then I'm going to go ahead and subtract 3 from both sides. So I get negative 1.535. So that's kind of our basics for how to solve an equation. We have to think about what the opposite or inverse operation is. Okay, let's try a few others. Let's do number 5. So 12e to the 1 minus x equals 500. So probably the first thing I would do is, again, just kind of like if you were to have, let's say in this scenario, if I were to have, 2x squared equals 200. You would tell me the first thing I would do is divide by 2, right? So then I would get x squared equals 100, and then I would square root both sides. Same deal here. We have 12e to the 1 minus x. Let's get rid of that 12. So let's divide both sides by 12 first. So 500 divided by 12 gives me about 41 2/3. I'm just going to keep this into my calculator. I'm just going to write it like this on my paper. So I'm going to keep this number, as you can see here. I'm just going to keep this number into my calculator. All right, now let's think about what the inverse operation of e is, right? So we have to get rid of this e so that I can get to this exponent. Well, the opposite or inverse of an exponential with the base of e is a log with the base of e. And so we call that a natural log, right? Log with the base of e is a natural log. So what you're going to do to both sides to get that to cancel is you're going to natural log both sides. So the natural log and the e cancel each other out. You get 1 minus x. And this is where your calculator is going to come into play. I'm just going to hit the natural log button, and then I'm going to hit second answer. Because you don't want to round here, you want to use all of the digits. So I'm just going to hit second answer so I can pull up all of those numbers from above. And I get about 3.73-ish. So 3.730. All right, let's finish solving for x now. So I am going to subtract 1 from both sides. And then I'm going to divide by -1. And that's what I get. So again, the thing that should be going through your head is, let's figure out what our inverse operations are. All right, let's now switch to log functions. So I have 2 and I have equals log base 3 of 4x. So what we're doing here is we want to get rid of this log. So just like with the exponentials, we have to think about, how do I get rid of the log? Well, the inverse of a log with a base of 3 is an exponential with a base of 3. So you're going to take an exponential with a base of 3 and do it to both sides. So it looks a little weird because you have to kind of do this, where you take the base of 3 and raise it to the left side, the base of 3 and raise it to the right side. That's how you're going to get this log base 3 to cancel out, because an exponential with a base of 3 and a log with a base of 3 will cancel, right? That's the whole goal. So you take that, whatever the exponential is, so in this case it's a base of 3, and you're going to take 3 and raise it to the left side and 3 and raise it to the right side. So I get 9 equals 4x, and then I get 9/4 equals x. Always check your work with a log function. So what you have to be careful for with logs is that when you plug it in, you can't have the log of a negative number. That doesn't exist. A lot of that has to do with the graph, right? So think about kind of like your graph where there's the asymptote there and it doesn't exist past a certain point. So does 9/4 cause this to be a log of a negative number? No, and so therefore I know that this is not an extraneous solution, so I can kind of use that one. All right, let's go on to number 9. So this has a lot of more stuff in it, but still kind of the same deal. This is a log with a base of 8, and then some expression equals 2/3. So I have to get rid of the log with a base of 8. This time I'm going to say, okay, well, the inverse of a log with a base of 8 is an exponential with a base of 8. So I'm going to take 8, raise it to the left side, and then take 8 and raise it to the right side. So it looks like that. Those cancel. I get x squared minus 5. You should be able to do this in your without a calculator. And just as a side note, remember when we did that, we separated the power from the root, right? Oops. And so it looks like 8 to the 1/3 squared. So the cube root of 8 is 2, and 2 squared is 4. So I just want to challenge you to not use your calculator in some cases, to use some mental math, because I think it's good for your brain cells. So anytime you have the opportunity to, please try. All right, we're going to solve this quadratic because there's an x squared here. So I'm going to add 5 to both sides, and I'm going to square root. So I get x to equal, don't forget your plus and minus, 3. You need to check both answers here. So if I plug in 3, does this give me a negative log? No, it doesn't. If I plug in -3, does it give me a negative log? And the answer is no, it doesn't, because -3 squared is still a positive number. So what I've concluded is that both of those answers are true answers, and therefore both of them work. All right, let's try number 11. So number 11 I like because they're throwing in kind of properties. So we're combining properties of logs with solving. So notice there's a subtraction sign in between. So the first step here is to condense, just kind of like if you had, you know, like distributive property on the left side of your equation or whatever, and you're asked to like simplify that before you start solving. Same deal here. So we're going to condense this into x plus 5 over x minus 2. So remember, when there's a minus sign, you're dividing whatever's in those two positions. All right, so now that we've condensed our log, then that was your first step. Next, let's get rid of the log with a base of 2. So how do I get rid of a log with a base of 2? The inverse is an exponential with a base of 2. So take 2 and raise it to the left side, and then raise it to the right side. So it looks like that. Again, we do this because our log and our exponential cancel each other out. So I have x plus 5 over x minus 2 equals 8. Easiest way to do this is probably cross multiply. So I'm going to make that as 8 over 1. And then I'm going to cross multiply. So I'm just going to write it up here because I'm running out of room. So I have 8 times x minus 2 equals 1 times x plus 5. So that's what it kind of gives me. This is just a linear function, so let's go ahead and solve for x. I'm going to distribute. I'm going to subtract x and add 16. I get x to equal 3. Check your answers. Does 3 cause either, go back to your original problem, not the one here, but the original one. Does 3 cause you to have any negative logs? Nope and no. So then this is a true example, not an extraneous. All right, let's do some other ones. So that was number 11. So I'll come back and do all the even problems here in a bit for those of you who are interested and want to check some work and try this on your own. All right, let's try page 183. So this is, we have a few other extra kind of problems here. So I wanted to go over these in a little bit more detail. So number 12 says solve the inequality. So we've done this with like other types of functions, right? And so why not do that with a log? So we're going to solve this the way that we would like solve an equation, right? So if this is a log with a base of 10, remember when there is no base, that's our common log, right? So that has a base of 10. So the inverse of a log with a base of 10 is an exponential with a base of 10. So I'm going to take 10 and raise it to the left, and have 10 and then raise to the left side and 10 raised to the right side. So again, the goal here is to get those to cancel out. I get x is less than or equal to 10 to the 1/2 is like saying the square root of 10, which is approximately 3.16. I just put it in my calculator and got that. All right, so in theory, you would say, okay, I'm good here, right? I got x is less than or equal to 3.16. The problem is there's always a catch, right? Because logs can be have extraneous solutions, we have to limit where x can be. So in this case, x has to be greater than 0 in order for this to make sense. So our final answer here is x has to be less than or equal to root 10. I'm just going to call it root 10 rather than the decimal because it's more accurate. But it also has to be greater than 0. You can't have it equal to 0 because there is no such thing as a log of 0. And it can't be negative, which is why that we have to restrict this. So even though solving it only gave us this side, we have to go back because it's an inequality and think about where the restrictions are for this particular function. All right, let's try, so I know that one was an even problem, but that's okay. So we're gonna try number 13, and then maybe I'll let you do number 14, and then I'll come back and do that one in a bit for those of you who wanna try it on your own. This one is kind of a weird one. I don't think you would know how to do this one without me, which is why I'm gonna do this one together. It says your parents buy juice for your graduation party and leave it in their hot car. When they take the cans out of the car and move them to the basement, the temperature of the juice is 80 degrees Fahrenheit. The room temperature of the basement is 60 degrees, and the cooling rate of the juice is R equals 0.0147. Using Newton's law of cooling, which again, I had to look this one up, it's not like something I have memorized, how long will it take to cool the juice to 63 degrees? And so they're obviously kind of a real world example. I don't know, to be honest with you, I've done this before. I haven't ever used Newton's law of cooling to figure it out, but now maybe I will. So Newton's law of cooling is this weird looking formula. So let me write it down and then I'll explain it. So it's T equals T sub 0 minus T sub R, okay, times e to the negative RT plus T sub R. So again, not a real, friendly looking formula, not one that I would probably know on my own, right? All right, so I should probably give you some side notes here. What does T sub 0 represent? Well, this is our initial temperature, kind of like your starting value, right? Anything at 0 is kind of like your starting value. T sub R represents your surrounding temperature. In this formula, that's what these variables represent. And T represents the temperature that you want. Like, in other words, your goal. Like, we want it to be 63 degrees or whatever it is. So this is kind of my legend here, right? So I just kind of, so that you know what each of those variables represent. All right, let's plug in what we know. So we know our initial temp, right? It was 80 degrees. We know the surrounding temperature of the basement is 60. And the temperature we want is 63. So let's plug in 63 for the temperature we want. Our initial temperature was 80. Our surrounding temperature is 60, because that's how much the basement is going. Our rate is the negative's out in front here. The rate is 0.01, so 0.0147. And they're asking for how long. So what we're solving for here is T. We're solving for time. That's ultimately our goal. Plus, T sub R is that surrounding temperature again, which in this case is 60, because that's the temperature of the basement. So this is an ugly looking formula, but to be honest with you, all it is just solving an equation. So let's simplify where we can. 80 minus 60 is 20. E to the negative 0.0147 T plus 60. Let's subtract 60 from both sides, so get rid of this. So I get 3 equals 20 e to the negative 0.0147 T. Let's get rid of the 20. So 3 divided by 20 gives me 0.15 equals e to the negative 0.0147 T. All right, so now once we got rid of all the stuff, right? Now this is a little bit more manageable of a problem. How do we solve this? This is an exponential because it has an e raised to a power. An exponential with a base of e. So to undo this, or to do the inverse, you would natural log both sides. So natural log both sides. So the natural log and the e cancel each other out. I'm going to put this in my calculator and I get negative 1.897 equals, and then I get negative 0.0147 T, and then I'm going to divide both sides. So I get 129.06 equals T, and I believe T is representing minutes in this problem. How long will it take? Yeah, so this is minutes. So even though that started off as a really ugly looking problem, to be honest with you, it was just kind of a solving exponential equation. All right, we are going to fast forward. I'm going to do 2 problems in 6.7, and then I'm going to come back and do all of the even problems for those who are interested. All right, so jump ahead to page 187. We've done some of this, at least in honors we have, and I don't know if in regular you have, but basically what we're looking at here are examples of like how you can tell from a function or from a table here what type of function it is. And so one of the things you want to look for is that, if you're looking for a rate of change or a constant rate of change, one of the things you would want to look for as x is increasing by a constant amount, okay, what is happening to y's? So there's a few things that you can look for. If your common differences are all the same, so that we call that our first differences, then we know that it's a linear function. If we have our second differences are the same, which means that if I do this and say, okay, then this is an increase of 13, this is an increase of 15, this is an increase of 17, and so forth. Then this would be quadratic. And then if the third difference are the same, it's cubic and so forth. So what we're going to kind of look at here is taking our second differences. So this is an increase of 2 approximately. This one was a little bit off, but that's okay. So what we notice is that if our second differences, so here's the first differences, here's our second differences. If they are the same, then we know it's quadratic. If the third differences are the same, that would be cubic. If the fourth difference is the same, it would be quartic, and so forth and so on. So I can tell you that this is a quadratic because the second differences are the same. So that's kind of how I know. The other scenario that you want to pay attention to is if it's not even any of those things, if it's a common ratio, or in other words, a common multiplier. So what I'm looking at here is what am I increasing by each time? If I'm multiplying by a constant amount, then we know that it's exponential. So if I'm multiplying, to get from 1/5 to 3/5, I am multiplying by 0.3. So again, to figure that out, you would take 3/5 and divide it by 1/5. To get from 3/5 to 9/5, I'm multiplying by 0.3, and then I notice that it is the same for all of these. So when you are multiplying by a constant amount, so put a little multiplication symbol here, then this tells me this is an exponential function. And so that's how you can tell from a table what type of function you're dealing with. This one is just, we've done this one before, but I'm going to go through one example, especially for those who maybe haven't seen it or just need a refresher. So we're given 2 points. We're asked to find the equation through those 2 points. So first and foremost, this is like what we did in sequences and series for my honors kids when we were given 2 different terms and we had to figure out, like we set up a system. So that's what we're going to do. We're going to say y equals ab to the x, and we're going to plug in the first point into this equation for x and y. So 2 equals ab to the -1. And then I'm going to take the second point, 32, and plug that into my equation for x and y. So 32 equals ab to the 3rd. So I have 2 equations with 2 unknowns. How do we solve this? Well, we go ahead and we use the substitution property. So I'm going to go ahead and solve for a here. So I get 2 over b to the -1 equals a. And I'm going to substitute this into my other equation in place of a. So I get 32 equals 2 over b to the -1 times b cubed. All right, here comes some simplifying, right? B to the -1 is actually just b. So this is like 2b times b cubed, which in other words is 2b to the 4th. Let's divide by 2. And now let's take the 4th root. So the 4th root of 16 is 2. So in order for me to write my equation, I need to have an a and a b. Well, I've got the b part, so that's good. Now let's go back up here and substitute in b so if we can figure out what a is. So 2 over 2 to the -1 equals a. Bring this up to the top because we don't want a negative exponent. So I get 4 equals a. All right, I've got my a and my b. Let's write our equation. So y equals 4, 2 to the x. And that's all you're really doing for all 3 of these, other problems here. So I would check your answers. I would try these on your own and check your answers. So I'm going to give you the answers to all of these just so that you can go back and practice and then check your answers when you are finished. So number 3, I've got an answer of y equals 4, 3 to the x. Number 5, I got an answer of y equals 1/4, 6 to the x. And number 6, I've got y equals 1/2 and then 1/2 to the x. So I would check your answers on those, and that way you can kind of see if you're doing that correctly. All right, this time, if you feel like you're good, you can go ahead and practice this. I'm going to go back and do the problems that are the even problems that are on page 182. So for anyone who wants to practice those, pause the video and then come back and check to see if you've got these correct. All right, so even problems. Let's do this. So number 2. So there's a whole bunch of different kinds of solving, right? So that's why it's good to kind of practice a variety. So this is one where, like how I explained with number 1, how you had to have the same base. Number 2 is kind of one of those where you have to have the same base. So what I'm going to do is I'm going to change both of those to have a base of 2. Because otherwise I don't know how else I could do it, right? I don't have, I can't change 4, or 8 to a base of 4, I should say. So I wrote that as 2 squared for 4, and I wrote it as 2 cubed for 8. So now I'm going to multiply those exponents. So I get 4x minus 2, and I get 3x plus 6. Now that I have the same bases, I can set my exponents equal to each other, and I get x to equal 8. All right, number 4. What I did with number 4 is I rewrote this one as a fractional exponent. So I did 1/5 to the 3/2 minus 2, and then I did the square root. So I did 25 to the x raised to the 1/2. So what I was kind of looking at here is rewriting these as the same base. So I'm sure there's a few different ways to do this problem. So I rewrote 1/5 as 5 to the negative 1. And I rewrote 25 as 5 squared. And so now I get 5 to the negative 3x plus 2, and then 5 to the x. So what that allows me to do is now have the same base, so I can set my exponents equal to each other. So I get 2 equals 4x, or x equals 1/2. All right, let's try number 6. On this one, I'm going to go ahead and get rid of the 14. So I'm going to add that to both sides. I'm going to divide by 3. So I'm just going to keep this answer in my calculator. I get 8 1/3, but I'm going to go ahead and just write it on my paper like this. The inverse of e is a natural log, so to get rid of the e, you have to natural log both sides. Again, keep that in your calculator. Those cancel. So natural log of 8 1/3 gives me approximately 2.120. For number 8, notice they both have a natural log on both sides of your equation, so the only thing I really need to do is set those two exponents equal to each other. So I'm going to get x squared equals 1. I get x equal 1 and negative 1. So check your answers, make sure both of them work, especially with a log function. If I plug in 1 for x, do I get a negative or 0? Nope. If I plug in negative 1, do I get negative or 0? Nope. So those are going to work. Number 10 is going to use some properties of logs. Notice that you have 2 different natural logs on this side. So you condense these first by multiplying the x times x plus 2. So it looks like that. Now they both have a natural log on both sides of your equation, so if we just set our exponents equal to each other, then we should be able to solve. So I'm going to distribute. Looks like it's going to be quadratic. So I'm going to go ahead and set this equal to 0. So I'm going to subtract x and subtract 6. So I get that. And now I'm going to factor. So this would give me positive 3 and minus 2. So numbers that multiply to negative 6 but add to positive 1. So I get x to equal negative 3 and x to equal positive 2. All right, I'm going to check my work. If I plug in negative 3, do I get a negative log? And I do. So this one is extraneous. I'm going to cross that one out. If I plug in 2, do I get a negative or 0? And the answer is no, so this one is a true solution. All right, the only other one I wanted to do is number 14 on page 183, in case you wanted to do that story problem with me. So this one's talking about earthquake intensity, which is probably the most applicable part of logs. So it says it's measured by a formula of R equals log of I over I sub 0, where I is the Richter scale rating for an earthquake. You've probably heard that, right? I is the intensity of the earthquake, and I sub 0 is the intensity of the smallest detectable wave. In other words, like what kind of normal waves we can see in the equation or in the world. In 1906, an earthquake in San Francisco had an estimate measure of 7.8 on the Richter scale. In the same year, another earthquake had an intensity level 4 times stronger than the San Francisco earthquake, giving it a Richter scale rating of R2, which just means another one, of log of 4I over I sub 0. What was the Richter scale rating on a scale of 1 to 10 of the other earthquake? So the first thing we have to do is figure out, if we're trying to figure out we have to figure out what the intensity is in order for us to figure out what the rating is. So we're going to start by using our Richter scale formula. So R equals log of I over I sub 0. And so the one we knew in 1906 had a Richter scale rating of 7.8. And so what we're going to do here, I'm going to put this in parentheses, we're just going to solve this equation. So we want to figure out what this is. Okay, so I'm going to get rid of this log. So how do I get rid of a log with a base of 10? Well, I do an exponential to a base of exponential with a base of 10 to both sides. So those cancel. I get 10 to the 7.8, whatever that answer is, and I get I over I sub 0. I'm going to leave it like this. So I'm not solving for I or I sub 0 because in my original equation, notice, or in the next equation, I have an I over I sub 0. So I'm just going to leave it like this. So now I'm going to take my next equation. This is the second earthquake. So R of 2. And it's log of 4I over I sub 0. What I want you to remember is that this is an equivalent way of writing 4I over I sub 0 is like writing 4 times I over I sub 0. And so that might make it more, I don't know, might make it easier for us to kind of understand. So what we're going to do here is we're literally just going to use the substitution property. So I'm going to substitute in, since this is I over I sub 0, I'm going to substitute in 10 to the 7.8 on this side. And then I'm going to throw all of this into my calculator to figure out what my Richter scale rating would be. If I do that, I get a Richter scale rating of 8.4. So even though the earthquake was 4 times as strong, the Richter scale rating isn't 4 times as big, right? So the Richter scale rating went from a 7.8 to an 8.4. But so that tells you the intensity of your earthquake, how much it grows from, like, if you have a 7.8 to an 8.4, how much, that means it was 4 times as strong. That's a rather large difference. So when you hear about earthquakes and you hear like, oh, it was a 6.2, and you hear another one, it was a 7.1. Even though that doesn't sound like a very large difference in value, in terms of intensity, it is. All right, that's all I have for now. Hopefully you guys did well. If you have any additional questions, feel free to bring them to class and practice what we have posted on Big Ideas. All right, bye for now.